Hey guys, welcome back for another chemistry lesson. This video is on ionization energy periodic trends. So first we need to define what ionization energy is. Ionization energy is the minimum amount of energy needed to remove an electron from an atom or an ion. We always measure this in a gas state, and it is an endothermic process. We have to put energy in order to remove an electron. So our valence electrons are the easiest to remove. They'll have the lowest ionization energy, and it looks like this. Right? So we have whatever it is in a gas form, plus the amount of ionization energy that we put in. So stuff, energy goes in, electron is removed, and now we have a 1 plus ion and 1 electron. Right? So we can then remove a second electron. So we'll have our 1 plus ion in a gaseous state, input the ionization energy there, and then have our 2 plus ion plus another electron. Right? The first ionization energy is the energy to remove an electron from a neutral atom, while the second ionization energy is the energy to remove an electron from a 1 plus ion. And then we also have third and fourth ionization energies, but that's generally more than we need to talk about. So the general trend for first ionization energy is the larger the effective nuclear charge on the electron, the harder it is to remove. And then the further away the electron is from the nucleus, the easier it is to remove. And those two things are related, but they're not the same. So our first ionization energy decreases as we go down a group, because as we go down a group, our atom is getting bigger and bigger. By adding principal energy levels, further out, easier to remove. And then generally, our first ionization energy increases across the period because our effective nuclear charge is increasing. This is related to our conversation about atomic radius, but specifically, it's also related to electronegativity. Because if you remember, and I'll put the video up here, for electronegativity, the stuff on the right-hand side of the periodic table wants to take electrons, not give them up. So it's harder to remove an electron from something that would rather not give up electrons at all. So again, effective nuclear charge increases across the period, so our ionization energy increases across the period. Here we can see ionization energy in graphical format as we go across a period. Yes, across a period. Sorry, had a moment. As I go across a period, the first ionization energy generally increases, like a lot. You will see that there are some exceptions in here, and I will talk about those in a later slide, the exceptions and why they're weird. And then as I go down a group, generally decreases, although there's not much of a change here at the beginning. There's definitely a pretty obvious change for our noble gases. Right here you can see the actual values of the ionization energies for first ionization energy, and you can see, generally speaking, as we go down, we decrease as we go down the group, and then generally increase as we go across the group. So the reason for this is the strength of the attraction of that electron to the nucleus is related to the most probable distance that that electron is from the nucleus and the effective nuclear charge that exists and is acting upon that electron, right? So the larger the orbital an electron is in, the farther its most probable distance and the less attraction it's going to have for the nucleus. So quantum mechanics predicts that our first ionization energy should be lower as we go down a column. All right, as we go across a period from left to right, the effective nuclear charge is increasing. So again, quantum mechanics predicts that the atom's first ionization energy should get larger across the period because we've got a bigger charge trying to hold in those electrons, and you have to undo that in order to ionize the atom. There are some exceptions, and I mentioned those before. The specific transitions that are exceptions are from 2A to 3A and from 5A to 6A. All right, so the difference between 5A and 6A you can see here, right? N is in 5A, O is in 6A, right? You'll notice that we have this paired electron here and this set of unpaired electrons here. To ionize nitrogen in this lovely place right here, you have to break up this half-full sublevel, and even though it's only half full, this is actually pretty stable, and it costs extra energy to break that up. Oxygen, on the other hand, has a half-full sublevel plus 1. So it's actually pretty easy to remove that electron. So that is why we actually see a little shoop, because we have a lot of energy and then it drops a little bit, because going from this to this essentially stabilizes it some more. All right, so successive ionization energies. As we remove extra electrons, it costs more energy. And the reason for this is we have more protons than electrons, so we're gripping in our electrons tighter. So our outer electrons move closer and are being held harder. They are harder to remove. And there's a regular increase in energy for each successive electron that's removed, and then we see a large increase in energy when core electrons start to be removed. So for sodium, we have one valence electron. So the first electron, very easy to remove. But then there's this big leap because I'm now trying to remove an electron from a full shell. That's why you see this gigantic leap from first ionization to second ionization. For magnesium, I've got two valence electrons. So the first two are relatively easy to remove. And then the third one is really hard to remove because now I'm at the point of trying to remove core electrons. And we can see that whole core electron thing I just talked about here. And this is just one period across the periodic table. And it's based on number of valence electrons, right? So relatively regular increases and then boom, big increase. Relatively regular increases and then boom, really big increase. So once you get to the point of trying to remove core electrons, there's going to be a massive jump. This is how we figured out that, well, not we, I didn't do it. This is how scientists figured out that there has to be a difference in like how the electrons are arranged, and there's got to be orbitals and all of that stuff. So this was really, really important data to get us to where we are now with our knowledge about atomic structure.